Hi everyone. Today we'll be taking a look at two more concepts. So we'll start with the first one, which is the types of events. Okay. So I'm sure you've already taken a look at this. I'm sure you've already studied this, but again, just for a quick revision and just to clear up any terminologies which you may be confused about. So I thought, we can just have a quick look at the basic terminologies that are used for majority of the probability questions. Okay, so let's start with number one, right? Number one is our event. Okay, so event is simply defined as it is a subset of a sample space. Okay, all right, an event is like the occurrence of an activity. Okay, the occurrence of an activity. In this situation that the example that I've taken is getting an odd outcome in throwing a dice. Okay, so in A is all the events that can possibly take place, right? So I have taken 1, 3, 5 based on this given situation, and the total sample space here is 1, 2, 3, 4, 5, 6. Obviously, because there are 6 faces to a dice, and each face has a number from 1 to 6, so that's how the idea works. Again, just a basic terminology, nothing too fancy, no rocket science. Let's go to the next one now. Okay, so next one, number two, is equally likely events. As the name suggests, right? It's quite obvious, I don't really need to explain much about it, but events are equally likely if they have same probability of occurrence. Okay? So, before I even get to this example, the first, fastest thought that comes to my mind is, flipping a coin. Okay? Flipping a coin. Right? Where you have heads or tails, right? And if you flip what we call in probability a fair coin, right? The possibility of getting either heads or tails is 50-50, right? It's the same. Similarly, in this example that I've mentioned here, we have getting odd outcome and getting an even outcome in a single throw of dice. Well, yeah, obviously you have 1, 3, and 5 in the odd outcome, and getting an even outcome is 2, 4, and 6, right? So there are 3 possibilities here, there are 3 possibilities here out of the total 6 possibilities, and that's why they're equally likely. Okay, let's go to the third one, mutually exclusive events. Now, the first thing that you might remember from your data booklet is you'll see the formula given for mutually exclusive, where they have mentioned probability of A union B is equal to A probability of A plus probability of B, right? This is what you probably have seen, and this is how you probably, uh, you know, correlate mutually exclusive, right? And then you're also told that obviously probability of A intersection B is 0. Now let's get to the root reasoning behind it. Okay, so when are events actually called mutually exclusive? Well, they're actually called if any one of them prevents the occurrence of all others. Okay, what does this mean? Well, let's say you're throwing a dice. Okay, so if you're gonna get an odd outcome, okay, you cannot get an even outcome. Okay, so getting an odd outcome and an even outcome while throwing a dice is impossible, right? It's impossible. Similarly, getting flipping a coin and getting heads and tails, it's impossible, all right? What's more mutually exclusive? What are the things that that can come in mind? Well, oftentimes, you know, having long hair and short hair, right? Is mutually you can't have long and short hair. Like if you go to the barber shop and you tell them I want my hair short, then you're gonna get a short haircut, right? If you just want to trim, then you're gonna have longer hair. So this is mutually exclusive as well, right? It's either A or B, right? Think of it like this: either A or B. Okay? For example, let's say you go to Subway, right? The first thing the person will ask you at Subway is what type of bread do you want? You want honey oats you want honey oats, you want Italian, you want Parmesan oregano, Parmesan oregano, right? And so on and so forth, right? And you have to choose either one of them. So it's either honey and oats, either Italian, either Parmesan oregano, or the 2 or 10 other type of breads you have. You can only choose one. So right. So in this situation, it's either A or B or C or D, depending on the possibilities. Right. That's what exclusive means. Right. It's only for one. Only choosing one. Right. This is only exclusive to one choice. That's how it is. You can't get half of the bread is Italian and half of his honey oats. You can't do that. It's only one type of bread. Okay, I hope that's cleared. So let's go to the fourth point that I want to address now is exhaustive set of events. Well, in normal English, exhaustive or exhausting means to be tired, right? To be tired. Oftentimes you're drained. When you're exhausted, you're drained of energy, correct? Right? You have nothing left in you. Nothing left. Nothing, no energy left. Nothing left. Okay? It's the same idea, okay? So if a set of events A, B, and C is such that their union is the sample space of the random experiment, then the event is called exhaustive set of events. Okay, there's a lot of words here, and if this is the first time you're actually looking at this, it can get quite confusing. So let's draw it out. Okay, uh, here I have 1, 2, 3. Okay, a Venn diagram of 3 events. Okay, A, B, and C, and this is my entire sample space. Okay, now let's say what basically what it's saying is for an event to be called exhaustive, all the possibility of occurrences have to be within A, B, or C. They can't be in the shaded area, which I'm shading in blue right now. If it's not in blue, it's only in the shaded area of yellow, then it's called exhaustive. You have taken account every single possibility and nothing is left out. Okay? For example, in a single throw of dice, getting an odd outcome, getting an even outcome, or getting a prime outcome. It's exhaustive. Okay? Why? Let's take a look at it. Okay? What are the possibilities of getting an odd outcome? Odd outcome 1, 3, 5. Okay. Then you have 2, 4, 6 for even outcomes. What are the prime numbers? Well, they are 2. Don't take 1. Okay, there's 3, and there's 5. Okay, so you've exhausted all the samples. Well, the sample consisted of 1, 2, 3, 4, 5, 6, and you have already 1. You already have 2, 2, 3 is taken, 4 is taken, 5, 5, and 6. You've considered all the possibilities in the sample space. That's why it's called exhaustive set of events. All right. I believe this is our final terminology, final term that I wanted to get over, get across, is independent events. Okay, so let's break it down. What does independent mean? Well, obviously it means not dependent, if that's the first thing that came to your mind. But what does not dependent mean also? What does independent mean? It's not relying on anything, right? It's not affected by anything. Not affected by anything. Anything. Or you can say not influenced, right? Not influenced, right? No matter what happens in the previous event, the following events are not going to be influenced by it. Okay. Before I get to the example, let's look at the definition, and then let me give you another example. Okay. So events are said to be independent if the happening of one event is not affected of others, right? That's exactly what I said, right? Let's say there are 3 events that have happened: event A, B, and C. Let's say event A, something has happened; event B, something has happened; and event C, we don't know what's gonna happen. But we've told that each event is independent, so we know that what's happened in A and B won't be reflected on C. Okay. For example, let's say you're flipping a coin 3 times. Okay. You're flipping a coin 3 times, and the first 2 occurrences you've gotten heads and heads. Now, if you're flipping a fair coin in a fair manner, okay, these are the assumptions I'm working with every time I'm solving probability questions, okay? So if I'm flipping a coin 3 times, for the first 2 times I've gotten heads. Is the third flip going to be influenced by whether I've gotten heads in the previous 2 times? Well, no, it's not. Because flipping the coin the third time has nothing to do with how I flipped it, right? I remember I flipped it in a fair manner without any sort of bias and any sort of anything that could influence it. So getting a heads or a tails is 50-50, right? It's a 50% chance I'm going to get either one of them. And this is why flipping a coin comes under independent events. Independent events. Okay, let's look at this example. If 2 dice are thrown together, then getting an even number on first is independent to getting an odd number on the second. Well, think about it. I have 2 dice, okay, like this, right? 2 dice. Okay, and another one here. Okay, and I get, I'm looking at this front face right here that I get, right? So here I've gotten a 1, here I've gotten a 4, right? If I'm going to roll both of these dice together, okay, there is no influence that they're going to have on each other. It's not like they have, some godly magnetic properties or magnetic fields that are being emitted causing them to have the same number, right? It's completely independent. The number that I got on the first dice is not going to influence what I get on the second dice. That's why they're called independent, right? Let's say you have 2 friends, right? Person A and person B. Okay, and not even 2 friends. They're just 2 classmates who have never spoken to each other, never interacted with each other, right? They sit in the opposite corners of the classroom. One sits on the left side, one sits on the right side. Okay, so what student A gets on his math test is not going to be influencing what student B gets on his math test. It never will. It can't because they don't know each other. They have no relation with each other. Okay? I hope that makes sense. Okay, so now we're on to the next part, which is called the addition theorem of probability. The name sounds really fancy, but I'm sure you've come across these things previously as well, so it should be a good revision if you have forgotten it. Okay, so before we start with like the formulas and the special cases, let's try solving this question. Okay, so if you want to, you can pause this video and give it a shot. So we're told that a card is selected from a deck of playing cards, and then find the probability that it is a red card or a king. Okay, so for those of you who don't know, there are 52 cards in a deck. Okay, cards. Okay, in total in one deck. Okay, out of that we have 26 red, 26 black. Okay, and there are 4 suites. Okay, 4 suites, 4 suits, 4 suites. I'm not exactly sure. I think it's 4 suits. If I'm wrong, I'm sorry. But yes, there are 4 suits. You have your heart, you have your diamond, you have your clove, and I think it's spade. Like this. Okay. All right. There are 13 of hearts, 13 of diamonds, 13 of cloves. I'm not sure, and 13 of spades. Okay. Now with this information, I think it should be a lot easier for you to solve. Okay, and there's a king, queen, and each number has each of them. So 1 to 10 plus jack, queen, and king, giving 13, 13, 13. Okay, so let's break it down now. So we have a red card. So we know there are 26 red cards. Okay, so red is 26. How many kings are there? There's 4 kings. Okay, so now I have my answer, right? I'm going to do 26 plus 4, which is 30, and then I'm going to divide by 52. And that's my final answer, 15 by 26. Is it? Think about it. And think about it really hard once. Because what I've done is I've made one small error in this situation. Okay? I've taken account for 4 kings, okay? Which account for red heart, red, I think, diamond, diamond, heart, and then black spade and clover. Clover? Yeah, I think it's a clover. Clover. Okay. So I've already accounted for these two red in this case. Okay, so I actually have to subtract by 2 to remove the double count. I've double counted them because they're already here, and then I've done it here again. Okay, so what I really have to do is I have to do 26 plus 4 minus the 2 for the red kings, because they're red and king, they're both, right? So I have to remove them. So now I'm left with 26 plus 4, 30, and then 28 by 52. If I divide by 4 again, I get 7 by 13. So this is my probability. Okay, again, let me just repeat what I've done here. So I'm told that either it's from the red card or it's a king. So I know there are 26 red cards, right? And I know there are 4 kings. But there is a common, similarity and overlap between both of them, and that is red kings. And I know there are 2 red kings. So I'm going to have to subtract them because I've already counted them once in either here or here. It doesn't really matter, but I've already counted them for once. That's why I have to subtract them. And that's why I'm doing 26 plus 4 minus 2. Divide by the total number of cards. Okay, so with this logic, let's look at the different situations that we can get in Venn diagrams. And normally you're only going to be facing Venn diagrams with either 2 or 3. Okay, nothing more than that. All right, so this is the first formula. Okay, addition theorem of probability, and it's saying that a union, okay, A or B, is equal to the probability of A plus the probability of B minus the probability of A intersection B. It's the same formula as the ones that you might have seen in set theory. Okay, I've just divided it, the formula from the set theory, by the total sample space. That's it, and then I get my probability. Okay, so let's draw it visually. Okay, so I have my first here, event A, event B. Okay, and this is my overlap. Okay, and let's draw the border encompassing the sample space. Okay, like this. Now A union B, I'm gonna highlight it, or let me do it like this. Let me do this in blue. So this is my probability of A. Okay, similarly, this is going to be in purple, like this. Okay, now this area in the middle, right, is the overlap of blue and purple, which is my red. Okay, so what I've done here is to find the probability of either event A occurring or B occurring, I've added A and I've added B together. Okay, but remember, while doing this, I have double counted A intersection B. That's why I have to subtract it once, just like I subtracted in the previous question. That just like how I subtracted 2, because there is an overlap of red kings. Similarly, I have to subtract because otherwise I'll double count them. Okay, and you can test this idea out by taking in random numbers. Okay, you don't really need to take decimals. I know I understand this probability, but you can just take normal, natural, or whole numbers, and you'll get the better idea of this. Okay, so now what is A union B? It's everything that's in red, blue, and purple, right? It doesn't account for anything that's in green. Okay, the green part is not A union B. Okay, that is like the remaining parts, remaining space, which is just empty space, right? It's part of the sample, it's part of the set, but it's not part of the union. Okay, all right, on to the next one. Now this is for 3 Venn diagrams. Okay, let's draw it out. So I'm gonna draw little smaller circles here. Okay, 2 and 3. Okay, so I got my event A, event B, event C inside a set like this. Okay, now I'm told that A union B union C, right, which is going to be all the circles shaded, right? Let me use the laser here. It's gonna be this part, and this part. Everything inside the circles. Okay? How can I essentially get that? Okay, now I just want to forgive you. This is a mistake, and let me change it. Let me make it black actually, and hide it. Okay, that was a typo. All right. So how can I essentially determine A union B union C? Well, I'm gonna have to add probability A once because I have to account for everything inside. Okay, I'm gonna have to add B, right? Which is this, all of it, right? And then I'm gonna have to add C again because I can't leave it out. So C, like this, everything is C. Okay. Now what I've done here is I've kind of double counted them, right? I'm sure you got the idea of double counting now. So I've double counted this region, right? Because I've shaded with yellow and green, right? This area. And obviously purple's there, but we'll neglect it we'll just, overlook it for now. So that's why I have to subtract it once because I've already considered it once. So that's why I'm subtracting it. Similarly, B intersection C, this part, right? Green and purple, majority. Obviously yellow is there in the middle, but for now let's just look at green and yellow, green and purple. I've considered it 2 times, right? So I have to subtract it once. Similarly, for A and C, my yellow and purple, I have to subtract it once because I've overlapped them 2 times. Now what's happened is because I have removed them each time, like every time they've been overlapped, there's nothing left in here. This area is completely, devoid of any consideration. So I have to consider this area as well, right? Which is, let me change the color. Let me make it perhaps red, right? I have to consider this area as well, which is my A intersection B intersection C. Again, let me explain it. I have taken A, B, and C, right? And then I've removed A and B because I've overlapped it once, right? So there were 3 of them, right? So there was 1, 2, and 3. I removed it once, removed it twice, removed it thrice. That's why A union A intersection B intersection C, right? The middle part has been removed 3 times because they were added 3 times. So there's nothing left. That's why I have to consider it one more time. I hope it makes a lot more sense now. And I hope it makes a more of an intuitive sense of why this formula even exists. Because once you get the intuitive sense, you don't really need to refer to the handbook. You don't need to waste time flipping pages. You don't need to waste time memorizing. You can always derive this relationship without getting confused. Okay, let's look at a few cases now. Okay, so first case is if A and B are mutually, this is kind of, I don't know why it's B, but if A and B are mutually exclusive events, then A union B is equal to probability of A plus probability of B. Well, that makes sense if you remember what mutually exclusive meant, right? Mutually exclusive meant it's either one thing or the other. It's not both, right? Both can't exist at the same time. You can't have a solar eclipse and a lunar eclipse at the same time. You can't have a full moon or a new moon at the same time, right? You can't have a sunrise and a sunset at the same time. I mean, technically you can, depending on the time zones, but if you're standing at one place and you're comparing whether it's a sunrise or sunset, it's either one. It's not going to be one and the other together, okay? So how would this look in a Venn diagram? Well, let's draw it out. This is my sample size, sample space, and this is my event A, and this is my event B. Okay. So what it's saying is probability of A and B occurring is 0, right? There's no overlap. Similarly, for this situation, you're going to have your sample space like this. A, B, and C, right? No overlap. So probability of A intersection B is 0. Probability of A intersection C is 0. Probability of B intersection C is 0. And obviously A intersection B intersection C is also 0. I hope that makes sense. All right. Now, let's look at some special cases, and these will really help you, churn your brain and get them thinking when you face something out of the box. Okay, so this is the first case where we're told that if A and B are two events of a random experiment, then probability of A minus B is equal to probability of A minus the probability of A and B. Okay, what it's essentially asking us, or what it's telling us, is if you just want to find the probability of a single event, right? Single event probability. And obviously the same thing can be applied for B as well. We can just swap A and B with each other and replace wherever A is there, we replace with B, and wherever there's B, we put A. But what is it actually saying? Okay, so let me draw a Venn diagram first. Okay, so let me draw a sample space like this, and let me draw two events, A and okay. So what it's really looking for, it just wants this area right here. Okay, that's all that it wants. It doesn't want the middle part. It doesn't want B. So how do you really get that? Well, now whatever I'm going to explain is going to be on the balance of keeping your books or maintaining your account. Okay, think of it like that. Let's say you and your friends go out to eat, and somebody pays for you, and then you have to pay them back, and things like that. Kind of like sort of that situation. You're trying to keep tabs of what's happening. What's coming in, what's going out. Okay, so let's say you want to find the probability of just this shaded region in yellow. Okay, now naturally, let's assume that it's not a mutually exclusive event, and it's not an independent event. Okay, so in that situation, okay, how can you do this? Well, what you can do is you can start off by finding the probability of A. Okay, well, to find the probability of A, let me erase this now. To find the probability of A, if you find the probability of A, you're going to be finding everything in A, which means the overlap as well. So it's going to be this complete area. Okay, this complete area. But now, if you just want what I had originally shaded in yellow, to get that, I have to subtract this middle part, right? I have to subtract this middle part. Once I can subtract this part, right? Once I can subtract this part, then I'm left with what I originally had in yellow, right? With what I originally had in yellow. That's how I am finding the probability of a single event in this case. Okay, I hope that makes sense. All right, let's go to the next question. Let's go to the next case or example. Okay, now we're on to the three events occurring at the same time. Okay, so if A, B, and C are three events of a random experiment, then what is the probability that exactly two of the events A, B, and C occur? Okay, we just care about two. We don't care about one. We don't care about three. We just care about two. Okay, so let's break it down again. Let me change the color, and let me draw a Venn diagram again. I have A, B, and C. Okay, like so, like this. Okay, so A, B, and C. Okay. All right. So what I'm really looking for is exactly two events. So my goal is just this part, and this part. That's all that I really care about. Okay? I don't really care about anything else. This is all I'm looking for. Well, how can I really find this? Well, let's look at what they've done here. They've taken A intersection B, which is this part. They've taken B intersection C, and C intersection A. That's all they've taken. Okay, and then they've subtracted it with the middle part. So how does that work? Let me erase this, and let's try to figure it out. So I've erased it now. let's take green in this case. So A intersection B intersection C and C intersection A. So that's just shading this area once. Then let me change the color actually so it's easier to observe. Then it's this area again, and it's this area. So if you look closely, I've just wanted what's in what I originally had shaded in yellow, but I have something in the middle as well. So that middle part is A intersection B intersection C, and that's what I'm subtracting. But I'm subtracting it by 3 times. Why? Because I've shaded that area 3 times. That's how I'm keeping the account. Okay, that's how I'm balancing what I've done and what I've not done. So because I've shaded it 3 times, so I've shaded it once with A intersection B, I have to remove it for that. Then I have shaded it. Then I've shaded B intersection C. I have to remove it again. And then for C intersection A, I have to remove that middle part again. And that's how I am removing, that's how I'm removing this area again and again and again 3 times so that this part is not considered. Okay, and that's how I'm getting the probability of exactly 2 events occurring. Okay, I hope that makes sense. All right, so with that, let's go to the final example case here that we're told that exactly one of the events A, B, and C is occurring. Okay, let's draw it out. What are they really asking for? Okay, so I have event A, event B, and event C. Okay, A, B, and C along with my sample space. Okay, so what they really want is this part, and this part. Okay, so how can we get this what I've shaded in red, right? I don't want the overlaps. I don't want a single overlap. I just want the independent regions. Okay, let's start. Let's start out by how we can actually generate that. Okay, so the way I can generate that is first I have to account for A, B, and C. Okay, so I have to, without any option, I have to account for A, B, like this, and C, like this. All right. Let me do one thing. Let me change the direction which I made the marks. Okay. So let me change the direction which I've made my marks. Let me make it, horizontal, vertical, and diagonal, like this. Okay. All right. Now, remember, I just want the independent areas of event A, B, and C. I don't want the overlaps. So I'm going to remove the entire A intersection B 2 times because one has been shaded by B, one set has been shaded by A. So I'm going to have to remove this area 2 times. Okay. Remember, keep an account. I've removed this area 2 times. So let me actually erase it now because I think I've made it a mess. Okay. I've removed this area 2 times. Okay. So now what's happened is I have removed this area. So now this is back to 0. Okay. This area is back to 0. That's how I wanted it. I wanted it to be empty because I've shaded it 2 times. So it was initially empty. Then I shaded it 2 times and now it's back to 0. Okay. And this area, and now this area is going to be same thing for here, back to 0 and back to 0. But I've shaded this area, this middle part in, let me change the color. I've shaded this area 3 times initially, right? And then I've removed it 2 times, 2 times, 2 times. So I've removed it by 6 times. So now I have a deficit of -3 in the middle. So how do I account for that -3? Well, I'm going to have to add 3 times again to get it to 0. And that's why I've added this A intersection B intersection C 3 times. So again, I've added A, B, and C, right? Because I have to account for them. Then I've removed them 2 times because I don't want a single overlap to be there. I don't even want one overlap. I want nothing. That's why I removed them 2 times. But now there's a deficit of -3 in the middle. And that's why I've had to add 3 again. All right. Now I know this can be really, really confusing at times. So if you want, you can always pause the video, or after this video, you can, draw it out on a piece of paper, draw it out, shade the regions, try to think about the balancing, keeping tabs, and then you'll understand that, okay, I'm accounting for the deficits. I need it to be zero. I can't have one. I can't have two. It has to be zero. Okay, that's how I've done it. All right, so using what we have learned up till now, let's try to solve a few questions. Okay, so give this question a shot and and then try and then see the solution again. Okay, assuming you've given a go at it, let's solve it. Okay, so we're told that A and B are events such that A probability of A or B occurring is 3/4. Probability of A and B occurring simultaneously is 1/4 or 25%. Probability of A not occurring is 2/3, and probability of A dash A or A complement intersection B is that's what we were told to, that's what we we're asked to find. So what is this actually asking us? Okay, I'm pretty sure this must have been the most difficult part in solving the question, because once you get this, then it's super easy. Okay, so what they're really asking us is, let's draw the Venn diagram out here. Okay, like this. A and B. All right. And they're asking us what's the probability of A intersection B, but it's A's complement. Okay. So A's complement. So what they're really asking us is just the probability of only B occurring. This is what they're really asking us. Because remember, A intersection B would be this part in the middle, right? It would be this part in the middle, right? Then it would be A and B, like, okay, so there would be just A and B, but now we're asking not A, okay? Not A. So it's removing this part and just the original shaded area in yellow, okay? So if they're just asking us this part, remember, I had shown how to find this, okay? What I said was this part, this is just the same thing as probability of B minus probability of A intersection B. So if we can find probability of B, and we're already told A intersection B is 1/4, so this is just 1/4, we can find our answer. Okay, so let's start with the addition theorem that we have. What we're told is probability of A or B is the same thing as probability of A plus the probability of B minus probability of A and B happening at the same time. Okay, so we know that A or B is 3/4. We can find out A because we're told A complement is 2/3. So probability of A is just 1/3. Because remember, it's probability of everything happening, but A is 2/3. Then obviously the probability of A happening is 1/3. Okay, so this is 1/3 plus the probability of B minus what's the probability of A and B? Well, that's 1/4. Okay, so it's like this. And have I done that correctly? Yes, I have. So this should be probability of B. Let me just check. I think I've messed up somewhere. So this is 1/3 probability of B. Okay, so yeah, this is gonna be 3/4 minus 1/4 minus 1/3. I apologize. This is gonna be plus. Okay, so this is gonna be probability of B is going to be 2/3. Okay, so now that we have that, we just have to do 2/3 minus 1/4. We'll just find the common denominator, 12, 8, 3, 12. And the probability of only B happening is 5/12, right? So super simple. Probably the hardest aspect of this question must have been figuring out what this is, right? What do they exactly want from us, right? So this is the main idea. If you do face difficulty in this, I think you can just take a look at multiple cases. You can just search up Google, different Venn diagram or set cases, and you can see that, oh, okay, A complement intersection B is just asking for B part. Okay, that's what it is. All right, let's look at another question. So we're told that if the probability of B is 3/4, the probability of A intersection B not intersecting C is 1/3. Similarly, again, it's another probability is 1/3. And what is the probability of B intersection C? Again, pause the video, give it a shot, and play once you have tried it out. Okay, so Best way to solve such questions is, again, by drawing a Venn diagram. So let's draw it out. So we have event A, event B, and event C. Okay, like such. Okay, so what have I been told? Okay, well, I'm told to find B intersection C. So my goal is to find this right here. This is my goal. How can I find this with the information that I've been given? Okay, so let me just erase what I've done, highlighted and shaded in yellow, and let's shade the areas that I've been given up till now. Okay, so I've been told that the probability of B is 3/4. So this entire shaded circle is 3/4. Okay, this part in blue. Now I've been told that probability of A intersection B not intersecting C is 1/3. Well, what is that exactly? What are they saying? They're actually saying you would think that A intersection B intersection C is this part in the middle, but now they're saying not C. So really, what they're saying is this part, just this part. So this is 1/3. Now, what are they saying about in the third expression right here? They're telling me that a complement intersecting B intersecting C complement is 1/3. Well, this area, believe it or not, is just this part, right? So now what you can see is the only area highlighted in blue is just what we're asked for, right? This part in blue is exactly what we want. So all I have to do is I just have to take the probability of B, subtract it with what I've done in yellow, subtract it with what I've done in red. That's it. So my final answer will conveniently just come out to be probability of B intersection C is just 3/4 minus 1/3 minus 1/3. So this is 3/4 minus 2/3. This is 9/12 minus 8/12, giving me 1/12. Period. That's my answer. Okay, so it seemed like a really, really confusing question, but I just broke it down by drawing what I know, right? Obviously, you have to understand what these expressions mean, right? Without them, it's really tricky to figure out what I can remove, what I can consider, right? But once I did that, it was super simple question, right? They told me that the entire B is 3/4. The shaded area in yellow is this part, which is 1/3, and then the shaded area in red is this part, which is another third, and I just want this blue part, right? So I can just remove the yellow and the red part, and I'm left with what I want. Okay, so with this question, I like to wrap up this video. So we looked at two major things. One was that were the terminologies, the terms that are somewhat important, especially in solving the question, because you don't want to have a brain fade moment during your exam. And the second part was addition probability. All right, so this was all for today's video, and I'll be seeing you in the next one. Bye bye.